This is section 14.7 on maximum and minimum values. Right, so on the bottom of page 959, it's maximum and minimum, just like in Calc 1 and 2. Here you have the XY plane and the Z value is the height. So you can see you have local maximum, local minimum, absolute minimum, just like in Calc 1 and Calc 2. So how do we find such points? Well, if you look at the maximum minimum values, if you looks like if you take the partial derivative with respect to x in the x direction, it should be 0. And the derivative in the y direction should also be 0. And that does turn out to be true. Right, so on page 960, here's the theorem, although you shouldn't really put this on your cheat sheet yet because you'll be putting it later on. But it does seem true. If f has a local maximum or minimum at a comma b and the first order partial derivatives of f exists, then fx equals 0 and fy also equals 0. Okay, so what you want to do is something called the second derivatives test on page 961. So you definitely want to put this on your cheat sheet. It's definitely harder than the second derivative test in Calc 1, you might recall. It's the second derivatives test. Okay, so suppose the second partial derivatives of f are continuous on a disk with center AB. Suppose that fx equals 0 and fy equals 0. In other words, you have a critical point. Then we define something called D. D is defined to be compactly fxx, fyy minus fxy squared. Okay, second partial with respect to x times the second partial with respect to y minus the square of the mixed partials. Okay, then follow these rules. If D is greater than 0 and fxx is greater than 0, you have a local minimum. If D is greater than 0 and fxx is less than 0, you have a local maximum. And by the way, that kind of feels like what we had in Calc 1. Second derivative positive, minimum. Second derivative negative, maximum. So that kind of fits. If D is less than 0, you have neither a maximum nor a minimum. Okay, you might have something called a saddle point. We've talked before about a saddle point. Here's figure 3. For the function z equals y squared minus x squared, you have a saddle point, because if you look at this direction, in other words, if y is equal to 0, you have z equals negative x squared, you have a maximum. But if you let x equals 0, you have z equals y squared, and you also have a minimum. Okay, so if you look this way, it looks like a parabola opening up, minimum. But if you look this way, it looks like a parabola opening down, maximum. Okay, and I guess this picture, wherever that happens to be, is a strange picture of a saddle point right here. I guess this hiker, it's kind of scary if you ask me, but if it looks like if you're going this direction, this would be a minimum, but if you look this way, it's a maximum. Okay. All right, so that's what you do to find maxima and minima. Okay, the text goes over a proof of it. You can look at it or not. Okay, so we'll be doing some problems involving that. Okay, now a little bit harder. Absolute max and min, page 965. First, we have something called a closed set. Okay, these two are closed sets. These sets are not closed. Think of a closed set as it's completely bounded. There's no way to sneak out. Okay, over here, dotted means you can sneak out. If you're here, you can sneak out that hole, or here you can sneak out certain ways. Here it's completely enclosed. There's no ways to quote unquote sneak out. Okay, so we have something called the extreme value theorem. We had that in Calc 1 also. If f is continuous on a closed bounded set in R2, then f attains an absolute max and an absolute minimum somewhere in the interval. Now in Calc 1, if we had a closed interval, okay, a closed interval is a closed set, okay, a continuous function in a closed set, you had to attain an absolute max and an absolute min, okay? And technique for doing that, page 966. Now you may recall in Calc 1, if you had a closed interval, you check for critical points inside, but you also have to check the boundary points, the two endpoints. Okay, so something similar happens here. Find the value of f at the critical points, find the extreme values on the boundary. Unfortunately, the boundary is not necessarily 2 points. The boundary might be an infinite set. In fact, normally it is an infinite set, like that square or that circle. So we'd have to analyze that. So that can get really long. Right, so The largest of these values from steps 1 and 2 is the absolute max. The smallest of these is the absolute min. Okay, so these problems can get really long, and I'll show you when we're doing that. That's on page 966. So you might recall in Calc 1, for the extreme value theorem, not only do you check the critical points on an interval, you check the two endpoints, left and right endpoints. Here, it's not just the endpoint, you might have to check an entire set. Okay, so here we go. 14.7, some homework. Page 967. And showing you that. And page 968. Problems there. And there. Here. Obviously, if you already have the text, you can just use the text. Yeah, problems 31 to 37. Those are the ones where you have to find the absolute max and min on a closed set. So those are going to be a little bit longer. Okay, and looks like a few word problems that we have to deal with over here. All right, so there we go. Okay, problem 5. F of xy is x squared plus xy plus y squared plus y. Remember, this is like z. Okay, find max and min. So first you find fx, partial with respect to x, 2x plus y, partial with respect to y, x plus 2y plus 1. Find fxx, 2, fyy, 2, fxy or fyx, it's 1 in both cases. Okay, so set fx equal to 0, fy equal to 0. So 2x plus y equals 0 means y equals negative 2x. So I put negative 2x right there. X plus 2 times negative 2x plus 1 equals 0. A little bit of simple algebra. So x comes out to be 1/3, y is negative 2/3. So the only critical point is 1/3 comma negative 2/3. Then I figure out the d. D is fxx, fyy minus fxy squared, which is fxx is 2, fyy is 2, minus 1 squared, that's 3, which is greater than 0. And fxx is 2, that's also greater than 0. So by our rule, we have a minimum. Okay, so the minimum value is f of 1/3, negative 2/3, which is negative 1/3. Okay, so we're using this chart over here. And again, put that on your formula sheet. This one, we had case A. Okay, so we're using this stuff. Okay, problem 11. F of xy is x cubed minus 3x plus 3xy squared. So fx, 3x squared minus 3 plus 3y squared. Fy, 6xy. Fxx, 6x. Fyy, also 6x. Fxy is 6y, which is also fyx. So now let's see. Fx and fy have to be 0. So 6xy equals 0 means x equals 0 or y equals 0. Plug in x equals 0 right here. Negative 3 plus 3y squared equals 0. Y is plus or minus 1. So we have 0 comma plus or minus 1. And y equals 0, put y equals 0. Then you have 3x squared minus 3 equals 0. That means x is plus or minus 1. So your critical points are plus or minus 1, 0, and 0 plus or minus 1. Figure out the d. Fxx, fyy minus fxy squared. Fxx is 6x. Fyy is 6x. Fxy is 6y quantity squared. 36x squared minus 36y squared. Okay, d at 0 plus or minus 1. If x is 0, y is plus or minus 1, you get negative 36. Those are saddle points. Okay, d of plus or minus 1, 0 is positive 36. Then fxx at 1, 0 comes out to be 6. That's a minimum. Fxx at negative 1, 0 is negative 6. It's a maximum. So here's an instance where we get all of these. Okay, f of 1, 0 is negative 2. That's a minimum. F of negative 1, 0 is positive 2. That's a maximum. F of 0 plus or minus 1 comes out to be 0. That gives me saddle points. Okay, 15. F of xy is e to the x cosine y. So fx is e to the x cosine y. Fy is negative e to the x sine y. Now, When is this 0? Well, e to the x is never 0. So that means cosine y has to be 0 and sine of y also is 0. Well, that never happens on a unit circle. So that can't happen. So there's no critical points, which means no max or min. So that's it for that one. Okay, then let's see. I'm going to jump all the way to problem 31 now. So you're trying to maximize or minimize on a closed set. Okay, so the set is defined to be bounded by 0, 2, 0, -2, and 2, 0, this triangular region. So I find critical points on the interior, and then I have to check the entire boundary. Okay, so here we go. Fx is 2x minus 2, Fy is 2y. Set them equal to 0. 2x minus 2 equals 0, and 2y equals 0 means you have to point 1, 0. F of 1, 0 is -1. Okay, so right here, 1, 0, the z value is -1. That's the easy part. The hard part is to analyze the boundary, which is that, and that. So I broke it up into 3 parts. You have x equals 0, y going from -2 to 2. This is y equals x minus 2, a little bit of algebra. You're going from 0, -2 to 2, 0. Slope is 1, y-intercept is -2. This is y equals -x plus 2, slope is -1, y-intercept is 2. So that's the 3 pieces that I'm considering. Okay, so if x equals 0, then f of y, put a 0 here and a 0 here, you just have y squared. Okay, well, when is that maximized? Well, it's maximized when you plug in 2 or -2, which is 4. Okay. And it's minimized when I plug in 0. So that function value is 0, but I already know right here it's -1, so it's not going to be lower than -1. Okay, so right now I have maximum at 4. Okay, along y equals x minus 2, x goes from 0 to 2. So x squared plus y squared minus 2x. A little bit of algebra. X squared plus x squared minus 4x plus 4 minus 2x, or x squared minus 6x plus 4. Okay, I know that's parabolic. Vertex is at -b over 2a, 6 over 2, which is 3, but that's outside of my range. Okay, so the maximum or minimum might be at the endpoints. Okay, so the endpoints f of 0, -2 is 4, f of 2, 0 is 0. Okay, so that means the z value, the height right here is 4, and the height right here is 0. Height right here is already -1. Okay, and I will do the same thing along y equals 2 minus x. So x squared plus 2 minus x squared minus 2x. Well, that's going to come out to be the same thing, x squared minus 6x plus 4. That's the same analysis as over here. So the maximum minimum might occur at the boundaries, endpoints. So once again, f of 0 plus or minus 2 is 4. Minimum f of 1, 0 is -1. We already have that. Okay, so height is 4, height is 4, height is 0, height is -1. So absolute max at f of 0 plus or minus 2, the height is 4. So right here and right here, we're 4 units up. And absolute min is at f of 1, -0, which is -1. So 1 unit down over there is what I have. Okay. Okay, 33. F of xy is x squared plus y squared plus x squared y plus 4 from -1, 1 cross -1, 1. So it looks like this. Okay. All right, so partial with respect to x, 2x plus 2xy, set it equal to 0. Factor out a 2x, 1 plus y equals 0. That means x is 0 or y equals -1. Fy is 2y plus x squared. Set that equal to 0. So let's see, if y is -1, y is -1, put -1 here, that means x is plus or minus the square root of 2. That's outside of my range, so forget about that. Okay, and if x is 0, let's see, x is 0 right here, that means y is 0, and f of 0, 0 is 4. Okay, so on the interior, the only critical number I have is 4. So now I have to check the boundaries, which are x equals -1, 1, and y equals 1 and -1. So y equals 1. So y equals 1 along the top, put y equals 1 there, y equals 1 there. So I get x squared plus 5, or 2x squared plus 5. Well, we know that's parabolic. Okay, so when I plug in 0, I get 5. When I plug in plus or minus 1, I get 7. So height is 7 here, 5 here, 7 here. X equals 1. So put a 1 right there, and right there I have y squared plus y plus 4 plus the 1. So y squared plus y plus 5. So the vertex is at negative b over 2a, negative 1 over 2. F of 1, negative a half, comes out to be 4 3/4. Okay, then I check the endpoints. If I plug in 1, 1, or 1, negative 1, then I get 7 here and 5 here. So the picture now looks like this. 7 here, 5 here, 4 3/4. I don't have to worry about, whoops, over here, 4 3/4. I don't have to worry about the 4 3/4 because that's not going to be a maximum. I already have a 4 here and a 7 here. Okay, for x equals negative 1, well, notice if I plug in negative 1 here or here, you get the same thing as if you plug in 1. So it's the exact same analysis. So nothing new under the sun there. So I still have f of 0, 0 is 4. F of plus or minus 1, 1 is 7 maximum. So 7 here, 7 here, 5 here, and 5 here. Okay, and then y equals negative 1. Y equals negative 1. If I put negative 1 here, negative 1 here, the x squareds cancel out. I just get a constant 5. So everything here is 5. Okay, so I have it, the whole thing analyzed. 7, 5, 7, 4. Everywhere constantly 5. And between 7 and 5 and 4 3/4, but never below 4. So absolute max are here and here. Absolute min at the origin. So f of 0, 0 is 4 minimum. F of plus or minus 1, 1 is 7. That is a maximum. Okay. All right, then 37. F of xy is 2x cubed plus y to the 4th. X squared plus y squared less than or equal to 1. So you're on a unit circle and the interior. Okay, so fx is 6x squared. Fy is 4y cubed. The only way they're both going to be equal is at the origin. So plug in 0, 0, you get 0. So the height at the origin is 0. Now along the boundary. Okay, well, for the boundary, let's see. I have y squared equals 1 minus x squared. So the function becomes 2x squared plus y squared squared, or 1 minus x squared squared. A little bit of algebra, that's x to the 4th minus 2x squared plus 1 plus 2x cubed on negative 1 to 1. Okay, so I'm trying to maximize or minimize that. F prime is this, which factors into this, which factors into this. So I try x equals 0, 1/2, or negative 2. Negative 2 is not under consideration in my domain. Okay, so x equals 0 on the unit circle. If x is 0, you have plus or minus 1. And if x is 1/2, you have plus or minus radical 3 over 2. So I plug all these guys in. Okay, so at 0 plus or minus 1, plug in 0 plus or minus 1, function value is 1. Plug in 1/2 comma plus or minus radical 3 over 2 is a little bit tricky. So put a half right here, either positive or negative radical 3 over 2 here, grind it out, it comes out to be 13/16. All right, so we have it. 0, negative 2, positive 2, 1, 1, and 13/16 is between negative 2 and 2. So we're done. F of negative 1, 0 is negative 2. That's the minimum. And here's the maximum. F of 1, 0, which is 2, is going to be my maximum in this particular case. All right, then some word problems. Number 41. Show you the context of that. Find the shortest distance from a point to a plane, 2, 0, negative 3, to x plus y plus z equals 1. Which means z equals 1 minus x minus y. So the distance, using the distance formula, it's x square root of x minus 2 squared plus y minus 0 squared plus z minus a minus 3 squared. Okay, but z is 1 minus x minus y. So put in 1 minus x minus y. I have 4 minus x minus y squared. So this is a d, but the same x and y which minimizes this will also minimize the square of that. So it's much easier to use f of x, y is x minus 2 squared plus y squared plus 4 minus x minus y squared. Okay, the same x and y which minimizes the square root of the distance is the distance rather is the same x and y which minimizes the square of the distance, which means get rid of the square root. Okay, then I just work on this. And we know that we're going to be minimizing, so that shouldn't be that big a deal. All right, fx, 2 times x minus 2 plus 2 times 4 minus x minus y times -1, set that equal to 0. Fy is 2y minus 2 times 4 minus x minus y, set that equal to 0. Okay, so a little bit of algebra. Let's see. Looks like that's the same as that. Since that equals that, that forces these two to be equal. So 2x minus 4 has to equal 2y. A little bit of algebra, y equals x minus 2. So 2 times x minus 2 times 4 minus x minus parentheses x minus 2 equals 0. 2x minus 4 minus 2 parentheses 4 minus x plus 2 equals 0. Clean up all the algebra. 6x equals 16, x equals 8/3. Y is x minus 2, so 2/3, and z is 1 minus x minus y is -7/3. All right, so 8/3, 2/3, -7/3 is the point that I want to over here, okay? And that's it. The last thing though is it asks for the shortest distance. So you have to actually use the distance formula now. So that minus that squared is 2/3 squared. 2/3 minus 0 squared is 2/3 squared. And then let's see, that minus that squared is also 2/3 squared. So that's 4/9 plus 4/9 plus 4/9, square root of 12/9. Okay, square root of 12/3. 2 radical 3/3 is the final answer. Okay, 45. Find 3 positive numbers whose sum is 100 and whose product is a maximum. So you're trying to maximize x times y times z. X plus y plus z is 100, which means z is 100 minus x minus y. So let f of x, y be x times y times z. Here's z. Distribute 100xy minus x squared y minus xy squared. So that's the thing you're trying to maximize or minimize. In this case, maximize. Okay, so fy, 100y minus 2xy minus y squared. Fy is 100x minus x squared minus 2xy. Fxx, -2y. Fyy minus 2x. Fxy, 100 minus 2x minus 2y. And then the big D, fxx, fyy minus fxy squared. So that times that is 4xy minus this quantity squared. Okay, so I set that equal to 0, fx equal to 0, fy equal to 0. Factor out a y, factor out an x. Now, if y equals 0, the product's going to be 0. That's not going to maximize it. Likewise, if x equals 0, the product is 0. Okay, if I set this equal to 0, that means 2x plus y equals 100. And if I set this equal to 0, that means x plus 2y equals 100. Multiply this equation by 2. 2x plus 4y equals 200. Subtract up. That minus that is nothing. That minus that is 3y. That minus that is 100. So y equals 100 over 3. Fxx is less than 0, which means you have a maximum. Okay, and then if you plug back in right here, yeah, but anyway, so x also has to be 100 over 3. I'll plug it into here, I guess, or here. Okay. And yeah, verifying the D. D comes out to be this, greater than 0, which is a maximum. Okay. And if the 3 numbers have to add up to 100, x is 33 1/3, y is 33 1/3, z also has to be 33 1/3. So they're all 33 1/3, 100 over 3. What are the 3 values? 100 over 3. Okay, separately, I'm just going to show you 17 because it's a little bit weird. F of xy is xy plus e to the negative xy. Okay, maximum, minimum. So fx comes out to be this. Factor out a y, 1 minus e to the negative xy. Fy is x plus negative x e to the negative xy. Factor out an x. Okay, set fx equal to fy equal to 0. One way is that either x is 0 or y is 0. Okay. And I figured out fxx is y negative e to the next negative xy times negative y, or y squared e to the negative xy. Similarly, fyy is x times negative e to the negative xy times negative x squared e to the negative x. And then the mixed partials, fxy is 1 minus e to the negative xy plus y times negative e to the negative xy times negative x, comes to be 1 minus e to the negative xy plus xy e to the negative xy. Okay, and just to double check, I did fyx, it came out to be the same thing. Okay, in this case, the d comes out to be 0 though. Okay, so d is fxx, fyy minus fxy squared. Okay, that comes out to be 0, which means the test fails. Okay, you can't do anything about the test. So how can you tell if you have a maximum or minimum? All you can do is just pick nearby points. Okay, so pick points nearby the origin. Okay, and if I pick points that are nearby the origin, okay, you're only going to get numbers that are larger. Okay, so I plugged in 0.1, for x and y, and negative 0.01. Okay, you get stuff that's bigger than 1. Okay, so the test fails, but we do have minimum values anywhere x is 0 or y equals 0, which is right here, the x-axis and y-axis. They're minimum because if I pick any nearby point, you try it out, and you see that you end up only getting numbers that are bigger than the function value of 1. Okay, so that's a little bit tricky for problem number 17. All right, so that was section 14.7.